Well, as Shannon was saying, this is the every month we have speakers, and it's the Free Westport Astronomical Society Science Lecture Series. And we always had people come in and talk to us, but lately and for the foreseeable future, we'll be doing it on Zoom. But Zoom opens up a whole different world for us because now, we used to just have people come from Yale or New York City but now you can have people from all over the world come, and we're really pleased with some of the people that we do have coming. Of course, Katherine Freese tonight, we'll get to in a second, but September 15th, Michael Turner from the University of Chicago will be joining us. And if you don't know who he is, he coined the term dark energy, which Dr. Freese is going to talk about a lot tonight, I'm sure. October 20th, this is going to be a great one. Professor Ron Mallett from UConn will be joining us, and it's the real science of time travel. So he had something terrible happen to him in his past, and he wanted to build a time machine. And so he is actually building a time machine. Fascinating guy. I'll post some videos that you can look at so that you're ready for the talk.
I already saw his talk.
What's that?
I already saw his talk.
Nice. I remember. Dr. Feldman. Priya Natarajan is coming from the Department of Astrophysics or Astronomy and Physics at Yale. She'll be here November 17th. And then Alex Filipenko will be joining us December 15th for the Big Wasp pre-winter solstice holiday party extravaganza party, like you just don't know what's happening. So that's all coming up on December 15th with Alex Filipenko. So we have all sorts of great speakers. And this month, it's my pleasure to introduce to you a brand new speaker that's never spoken at WASP before, has not had a visit at the observatory, but Katherine Freese. She holds the Jeff and Gail Kodosky Endowed Chair in Physics at the University of Texas in Austin. Previously, she was the George E. Uhlenbeck Professor of Physics at the University of Michigan and Visiting Professor of Physics at Stockholm University. She works on a wide range of topics in theoretical cosmology and astroparticle physics, and she has been working to identify the dark matter and dark energy that permeates the universe, as well as to build a successful model for the early universe immediately after the Big Bang. She's the author of The Cosmic Cocktail, 3 Parts Dark Matter. Please welcome Professor Katherine Freese.
Thank you for that kind welcome. And I just want to make a few comments first, which is, wow, you guys have a wonderful organization. You're doing such wonderful things. And I see you have some of my friends coming, like Mike Turner and Priya and great speakers you have coming up. And yeah. I also wanted to thank you. I learned something about women in astronomy. I'm friends with Jackie Hewitt and some of the younger women, but Wilhelmina Fleming was a maid because her husband left her with a baby. Oh my God.
What a story, huh? I remember that story. That's a good one. Thanks for that, Cal.
Oh, that is so impressive. I mean, so yeah, that's really, wow. I'm glad I don't have to live up to that one. But anyhow, so I guess I should also say I love the pictures that you showed. And what I'm talking about today is the stuff that you cannot see. So let me share my screen at this point. And I would like to make it full screen. So did I succeed in making it full screen? Somebody tell me if it looks okay.
Looks good.
Okay, so all right, in that case, I will plow on. I like to think about the modern field of cosmology in terms of human history. So throughout the existence of humans, people have been trying to figure out who we are, where did we come from, where are we going? There are different creation myths, and every culture had one. And about 100 years ago, we came up with the one called the Hot Big Bang. And the thing that is so phenomenal is that it is correct. It is incomplete, but the basic picture is correct. And so if you think about the progress that humanity has made in the last 100 years in understanding the cosmos, it's really mind-boggling. And it really all started with Einstein's relativity in 1915. Then very soon after that, other people applied the equations to the universe as a whole and made some sort of basic assumptions about how smooth the universe would be on large scales, and came up with 3 possible behaviors for the universe. It could be expanding, it could be contracting, or it could be static. And Einstein really liked the idea of a static universe because that would be additional symmetry where the universe would look the same on the average at all times. But along came Edwin Hubble, and the reality of nature trumps the elegance of any theory that you have. Now, he was working above Pasadena in California using the Mount Wilson Observatory. I had a sabbatical at Caltech, and I used to I could look up there from my apartment, but I didn't really get it until I tried to bicycle up there. So it's high up there, and a lot of amazing discoveries were made up there. So first of all, he was the first to show that there have to be other galaxies beyond our own, because things were just so far away that had to be true. And another major discovery that he made was by looking at galaxies at various distances away from Earth and realizing that if you look at the light that there's atomic transitions that we understand, so we know the light that's coming out of the galaxy. But then those waves were stretched by the time they got to us, kind of like this picture of a balloon. When you blow up the balloon, the wave stretches. And so the explanation for that is that the universe is expanding. So Einstein, although he had really preferred the static universe, had to give up on it because, well, the universe is expanding. This is a sort of a picture of that, where I'm showing galaxies on the average, all moving apart from one another. And that basically is what the Big Bang is all about. So the universe started about 14 billion years ago, at least the parts of the universe that we understand, in a primordial soup of particles. So on the right, you can see that they were all really tightly packed together at the beginning. We had the quarks that make up atoms, electrons, dark matter particles, everything the photons were all packed really tightly together, really, really hot, bumping into each other. And then as time went on, the universe cooled off and expanded. And that's what the arrow is showing, the downward arrow is showing here. Oh, I guess you can see my mouse, can't you? So I can use it. Oh, brilliant idea. So this is sometimes people call this a raisin bread model of the universe. So it's meant to be a mock-up of our expanding universe, where the raisins are like the galaxies. So if you take a loaf of raisin bread and you put it in the oven, then the dough rises, and the raisins are moving apart from one another, not because they're doing anything, but just because the underlying bread is expanding. And that's meant to be a model of what's going on with galaxies inside the universe. So I have never made raisin bread, but I'm sure it's true. But the difference between this raisin bread model and our universe is that, well, the raisin bread has a central point, but our universe, as far as we know, does not. There's no special place in the universe. So yeah, the Earth is not special, the sun is not special, the center of the galaxy is not special. So going back to the picture that I had before of galaxies expanding away from one another, no matter where you go in the universe, if you go to some other galaxy far, far away, then from that perspective, the other galaxies will still be on the average moving away from you. So you might be confused because you might think, wait a minute, we're supposed to merge with Virgo, or I'm sorry, we're supposed to merge with Andromeda, which is our neighboring galaxy, and that is true. So things that are really close together, where gravity wins over the expansion of the universe. So in the room you're sitting in, certainly gravity is winning over the expansion of the universe. The people have some misconceptions about the Big Bang that is promoted by many journalists as well. But as I wanted to talk about what is the notion of the Big Bang? Well, if the universe is expanding now, then if we can do the opposite, we can look backwards in time, and then everything gets closer and closer together. So that means everything in the room where I'm sitting, if you go backwards in time, yes, that would contract to a point. But what if the universe is infinite, which is very possible? Well, then no matter how long you go backwards in time, there'll still be something out at infinity. So you would not contract everything to a point. So even no matter how far back you go in time, still you would have an infinite universe, but it would get more and more densely packed, everything on top of everything else. And eventually the density is so great that our laws of physics fail. So then we would have to have a theory of quantum gravity, which we don't have. Maybe string theory kicks in at that point. And so that's what we mean by the Big Bang, is that we lose our ability to describe what is happening in the universe. So the Big Bang, well, first of all, it's not an explosion, but fine, let's have one. But if you did want to picture it that way, then you'd have to put an explosion everywhere in space. So you can think of the Big Bang as a point in time rather than a point in space. So it's not like everything came from one singularity, from one point in space. Well, so I mentioned that cosmology has taken off like crazy in the last 100 years. And so I wanted to sort of review, where do we stand? Well, a lot of big questions were answered actually at the turn of this millennium. What is the geometry of the universe? What is the total mass and energy content of the universe? How old is the universe? The basic picture for the growth of galaxies and other large structures. But a lot of big questions remain. How did the universe begin? What is the universe made of? And that leads to the question of what is dark matter and dark energy? So I did want to talk about what we have learned over the turn of the millennium, and that's about the geometry of the universe. So I mentioned at the beginning that there are three possible geometries for the universe. These are lower dimensional analogs, so we can't draw three-dimensional, higher dimensional objects, but we could be living on the universe could be on the surface of a sphere, which is this left picture. It could be like a saddle, or it could be a flat geometry. And again, this just means the geometry is flat, not that the universe is physically two-dimensional or anything like that. So at the time of post-Einstein, there were these three possible geometries, and what we've learned in the turn of the millennium is that the geometry is flat. And to show what I mean by this, we imagine we have this little guy sitting here. Well, if he's at the top of the sphere and he sends out two light beams, they look like they're diverging, but guess what? They're going to come back and bite him in the behind. Whereas on this guy, if it's a flat geometry, then two parallel light beams, they will never meet again. So two parallel light beams in the flat geometry just keep going, never meet again. Whereas I think I said I didn't say what I meant for the closed case. He sends out these two parallel light beams, and they're still coming out and getting him from behind. So it was the cosmic microwave background, which is the light left over from the hot early period of the universe, when the universe was 400 million years old. So there's leftover light, and it's from that we learn so much about cosmology. So this is the universe as seen in the microwave. There are these orange spots. Those are spots that are hotter than average, and the blue spots are cooler than average. And it turns out that the size of these regions, typical size of these regions, tells us about the geometry of the universe. So the typical size of these regions is actually 1 angular degree in size. And from that, we know that the geometry of the universe is flat. It's kind of a tricky argument. I don't really have time to go through it entirely, but I want to really make sure that I explain what I mean by flat, which is, as I said, the universe is not two-dimensional. Let's take a cube and imagine it goes to infinity in all directions. Well, but the shortest distance between 2 points is a straight line. There's just ordinary geometry with no curvature at all. And that is what our universe looks like. So we do not have a curved universe. So going along with the geometry of the universe, Einstein's equations relate that to how much stuff is in the universe. And the answer is 10 to the minus 29 gram per cubic centimeter. That's the average place in the universe. And just to compare to Earth, the water on Earth is about 1 gram per cubic centimeter. So that tells you that, well, that's really diffuse. So that is kind of one way to think about it. That's the density of outer space, as I tried to explain to the Queen of Sweden, and it was a bit of a fiasco. So feel free to ask about that story later. The trouble is that we don't know what that stuff is, but before I turn to that question, I have to have a little joke here. This is the same microwave background data, this leftover light from the Big Bang, and here we have SH, Stephen Hawking initials. So now I want to turn to this question of what the universe is made of, and this is it's really, if people have never heard about this, they're like, what? all the objects of our daily experience, our bodies, the chairs we sit in, the walls of the room, the cocktails, the sun, the earth, everything that we're familiar with, it's all made of atoms. But all of that adds up to only 5% of the content of the universe, which means we don't know what the rest is. So here's the ordinary stuff is 5% of the universe, the stuff we know about. The dark matter is about 25%, and the dark energy is the rest, about 70%. So the big puzzles are, here we are supposedly in the era of precision cosmology, but we don't know what 95% of the universe is made of. Okay, in my book, I had fun making a recipe. Oh, you can't see the edge of it. That's unfortunate. You know what? I think I'm just going to skip ahead on this for the cosmic cocktail recipe. But it's basically this picture here, that dark matter and dark energy make up most of the universe. So I'm going to talk, do you see this bar up here? Is this blocking your view, or can you see everything? I'm going to assume you're seeing okay, and if not, you'll interrupt me. But this dark matter problem it's one of the most difficult, outstanding problems in all of modern physics. It's an 80-year-old problem dating back to Knut Lundmark in 1930 and Fritz Zwicky in 1933. This is Fritz Zwicky was looking at galaxies in the Coma cluster, and he noticed that the ones at the outer edges were moving too fast. He couldn't explain it in terms of the gravity of the other galaxies that were farther in. And so he said, well, if there's something else providing a gravitational pull that's speeding things up, let's call, he was Swiss, so he called it dunkle Materie, which means dark matter. And by saying dark matter, that simply means it's not stars, it doesn't shine, it's dark. And I hear he was rather a cantankerous character. So in his book, he called his colleagues spherical bastards, because no matter what direction you look at them from, they're still bastards. So I'm glad I was not his graduate student. So there were pros and cons. People's arguing was, this is one observation, but then other people started seeing it, and it was really the work of Vera Rubin and Kent Ford in the 1970s that nailed this problem. The reason that it was so important is that their work led to scientific consensus that the dark matter problem is there in every single galaxy that they looked at. So they really proved it is a problem. And yeah, she should have gotten a Nobel Prize, but she died a few years ago in her 80s, so that can't happen anymore. But one of the major new telescopes coming up, the LSST, is now called the Vera Rubin telescope. So let's talk about the kind of work that she did by analogy to the solar system. Okay, now this has nothing to do with dark matter. I'm just talking about the sun and the planets. So this is a plot. On this axis, I've got the speeds of the planets, and on this axis, I've got the radius of the orbit of the planets as you move. 0 is the sun, and then as you move out, you're getting from Mercury, Venus, Earth, Mars, and so on. And you'll notice as you move out, the planets move more and more slowly. And this law tells you, this is the simple law of gravity, tells you how fast they're moving. And you'll notice that if you were to increase the mass of the sun, make it 4 times as heavy as it is, then everybody would be moving twice as quickly around the sun. So this shows the idea of what we call rotation curves, which is exactly what Vera Rubin did. She was not looking at the solar system, obviously, but before I leave the solar system, I love the stories about Tycho Brahe, who was another character. He lost his nose in a duel and wore a gold and silver replacement. Ew. But he did some of the most important studies of planetary orbits. Then there was a lot of discussion, how did he die? And so the story that I'd always heard is that he went to dinner with the king and had a lot of wine, and you're not allowed to get up until the king does. And a few days later, his bladder burst, and a few days later, he died. So I can attest to this because I got to go to the Nobel ceremony twice, actually. And sure enough, I was wearing my beautiful ball gown and and I went up to go to the bathroom. And when I came back, a woman who was a member of the Nobel committee was deeply offended that I'd gone to the bathroom because the king was still seated. I was like, to hell with it. If I gotta go, I gotta go. But anyhow, so I'm sorry to put it that way. But it got even funnier in his case, because then they were theorizing he was killed by mercury poisoning. By whom? By Johannes Kepler. You know Kepler's laws. Well, what if they should have been Brahe's laws and Kepler knocked him off? Kepler was his grad student. So they actually dug him up about 10 years ago, the body of Tycho Brahe, and they tested very sophisticated modern equipment and found no mercury poisoning. So we're back to the burst bladder at the dinner with the king. Hold on one second. I think I'm going to need more light.
You can do that.
Thank you. It's getting dark in here. Beautiful sunset, but I guess you'd like to be able to still see me with the galaxy behind me. So I'm moving too slowly. I'm sorry, but I'm having fun telling all these stories. So I hope you don't mind.
To be fair, we can't see
Now
you
I'm gonna
anyways.
leave
We
the
see your
subject.
slideshow. Most of us see your slideshow.
Okay. Oh, okay. So then I won't worry. Thank you. Well, so leaving the solar system and turning now again to the problem of dark matter. Now let's talk about galaxies. And I've got here the center of the galaxy with some star orbiting around it. And you can see how fast this star or this gas or whatever is moving around the center. And just like with the solar system, the more mass that you have more mass interior to this orbit means that the star is moving faster, okay? And so what they found was, whoa, these guys are whizzing around. They're hurtling around the center of the galaxies. And what in God's name is speeding them up? So it all works if you add a lot of dark matter interior to this circular orbit. This is a plot of a galaxy. It's just like that solar system plot. And this is what was expected to be seen. Here, 0 means the center of the galaxy. And as you move out, you're moving away from the center of the galaxy. So people thought, well, we'll see the same thing we would with the solar system. As you move out, things go slower. Nope. Whoops. This is a flat curve, a flat rotation curve, and that means there's more matter in there. And if you add in a galactic halo, then it all works. So then it would explain, you add in more matter and it all works. And so, well, this is the Milky Way. That the center, there's a supermassive black hole that weighs 4 million times as much as the sun. The galaxy as a whole weighs 1 trillion times as much as the sun. So the mass of the black hole is irrelevant in the grand scheme of things. And then coming out of that, there's a pinwheel of structure, and that along these pinwheel arms, that's where all the stars are. So when you look out into the Milky Way, there's some of those beautiful pictures that you showed. That's what you're seeing. You're seeing the stars along these spiral arms. But now let's take all of this and lay it on its side. And so the spiral arms are in this flat thing that we call the disk. And the center of the galaxy out to the sun, that's a distance of 25,000 light years, which means our sun is not feeling the effects of that black hole at all. And so if we go on to an artist's rendition of what the complete galaxy looks like, you've got these spiral arms and this disk where the stars are, but then most of the mass of the galaxy is in this thing that we call the dark matter halo. Don't ask me where the word halo comes from, but it is what it is. So that was the first way with these rotation curves that Vera Rubin nailed it down, that every galaxy has additional matter making things move really quickly. But let me turn to another way to detect dark matter, and that is Einstein's Lensing. This way of looking for dark matter was actually also initially proposed by Fritz Zwicky. So the idea here is that Einstein predicted that mass bends light. So if you have some mass sitting here, I don't care what it is, and I drew it for a massive compact halo object, but it doesn't matter, any dark matter, then you can't see the dark matter with your telescope, but what you can see is how it affects the stars behind it. So the light from the star would get bent towards your telescope. So you might think, well, you wouldn't know it was, since if you didn't know it was bending, you might think, well, the star's over there. But then you would notice two things. First of all, you'd notice, aha, there's another image. I have a double image, or sometimes even the most extreme case, if everything's lined up perfectly, you get that Einstein ring, which is what Jackie Hewitt first discovered. So you get multiple images of the same thing, or even a ring, and these guys are distorted and sheared. So the lensing makes multiple images, and it makes images look sheared. So, and here's a picture of how mass bends light. So at Earth here, when we look past the sun, then the star light is bent on its way to Earth. Okay, so this isn't necessary, but I have to, well, on your phone, there's an app for gravitational lensing, which was written by Eli Rykov, a University of Michigan graduate student. And it has the correct equations for gravitational lensing in there, so you can lens yourself. So here's one of my students lensing himself, if you put in more and more fake dark matter in the way, then you get more and more lensed. So that's kind of fun, something you can do. Well, here's some real data for dark matter lensing things. And so that what we're looking at here is a distant galaxy, and it's actually a cluster of galaxies with dark matter on the way. And there's a lot of lensing going on here, and I do not know the details, but you can see these sheared objects, the multiple sheared objects. And so you've got multiple images, you've got the shearing, and from the background light, the way it's bent by the light, by the mass in front of it, you can learn about the dark matter. So this one was using Hubble Space Telescope. So this is a different cluster using Hubble Telescope. After you look at your data, then you do a computer reconstruction of the mass that had to be in the way to produce the images you see. So in this case, these peaks are galaxies. So this tells you there's a lot of mass at this location. Okay, so these are galaxies. And in this cluster, it turns out there's even a smooth component in between the galaxies. So there's dark matter in the cluster, in addition to dark matter in the individual galaxies. So I could go on and on telling you about all the evidence for dark matter. I think I'm going to do one more, and that's the bullet cluster. This is a really important one because it really shows that you have two different types of matter. What we think is going on here is you have two clusters merging with each other. And when that happens, the atomic matter, which is shown in pink, gets stuck. So we see X-rays coming from this pink stuff, and that means it's gas, it's ordinary stuff. And it didn't get very far because atoms have strong interactions which hold nuclei together. They have electromagnetic interactions, which is also what causes things to give off light. But the dark matter, there's a second kind of matter, which is found by lensing, which is shown in blue. And so look at that different behavior. The dark matter just keeps going. So it feels gravity, which means eventually these two clusters, they're moving through each other, but eventually they're going to end up as a single object. But on the first pass of this collision, the dark matter behaved very differently from the atomic matter. So this is thought to really prove that there's two separate types of things going on. So I think I'm going to skip ahead in talking about the various types of evidence for dark matter. Everything I've talked about has to do with dark matter's presence through its gravitational influence, but what we want to know is about its non-gravitational interactions. And I haven't even talked about some of these other pieces of evidence for the existence of dark matter, but what I do want to turn to is the question of what is the dark matter made of? And so you probably heard about neutrinos, but they're only about, their masses are just too light. So they're only about 0.5% of the content of the universe. So they're not, the dark matter is not made of neutrinos, which is too bad because they exist. And that would have been great. In the 80s, people were hoping it could be neutrinos, but that just doesn't work. And here you have the different amounts of hydrogen, helium, stars, and other elements and what they contribute to the universe. So back in the 80s, people ran through some of the most obvious candidates. Could it be gas? Could it be dust? Could it be rocks? Could it be lumps of lumps or snowballs of hydrogen? But all of these possibilities would have had observational consequences that didn't pan out. So it's nothing simple. And what that leads to is a plethora of dark matter candidates. And I just wanted to point out that where you see names in red, here. These are the names of some of my students and postdocs, and I'm just trying to advertise the kind of the work. This is the kind of work that they've done. So as I said before, it can't be neutrinos. They're too light, and then anyway they would ruin galaxy formation. There's all kinds of other really interesting possibilities, including primordial black holes. But the top two candidates, though, they would be wimps or axions. And the reason that I'm putting them as the top two is because they were not invented to solve only the dark matter problem, but instead in particle theories, they already exist as candidates for reasons that have nothing to do with dark matter. So they're already there, and that is why people are really actively looking for these two candidates. And today I'm going to focus on the one that I've really worked the most on, which is WIMPs. So WIMPs stands for weakly interacting massive particles. In fact, these things really are weakly interacting. So they don't have the strong nuclear force or the electromagnetic force the way that the gas did in the bullet cluster that I showed you. Yes, they do feel gravity, but of the four fundamental forces, the only one remaining that would be the weak interactions as a possibility. And so if that's true, then billions of these things pass through your body every second. And we don't know exactly, but roughly one a day or one a month would hit one of your nuclei. So these things are weak interactions are also responsible for some types of radioactivity. So of the four fundamental forces, this was an interesting one to investigate. And these particles weigh about 1 to 10,000 times as much as protons. So one reason that we think WIMPs are interesting, as I said, is they're already there in particle theories. And as an example, there is supersymmetry you may have heard of. And in supersymmetric models, every particle we know has a partner. So if you have, these are all the particles of the standard model. These are the quarks, up, charm, top, and so on. These would have partners, supersymmetric partners. And when the twiddle is written over the top, that tells you it's the supersymmetric partner. And these partners are heavier than the ordinary matter that we're used to, which is why we haven't seen them. And all of them are unstable. They would decay until you got to the lightest one. It would be the lightest supersymmetric particle, which would be the dark matter. Now, because these things are heavy, you have to do something unusual. They're heavy and weakly interacting. They're not easy to find. So there's a number, three or four different ways that people are looking for it. And the first one is using particle accelerators. So this is the Large Hadron Collider at CERN in Geneva is a ring that's 17 miles around, this giant ring where you accelerate protons in opposing directions to nearly the speed of light, and then they collide at 4 intersection points where there are detectors. I have a picture of a few people working on this. One of them is Fabiella Gianotti. She was a spokesperson for 3,000 scientists of the ATLAS experiment, and now she's actually the director overall at CERN. This is the ATLAS detector, and look at this. This is a guy standing here just to give you an idea of how mammoth this detector is. It's very impressive. The other general purpose detector is the CMS detector. Here's Peter Higgs in front of that detector, and you may have heard of the discovery of the Higgs boson, the last missing piece of the standard model of particle physics. And this was discovered by this particle accelerator, and it weighs about 125 times as much as a proton. And it is the Higgs that imparts mass to other particles in the theory. But one of the second major goals of building this Large Hadron Collider was the search for supersymmetry and the search for dark matter. And you would see something like this when the two protons collide, a chain of dark matter particles of supersymmetric particles until the lightest one escapes detection. But at this point, nothing has been seen yet, which is disappointing. So particle masses are being pushed to higher and higher masses, and well, nothing yet. Now, there are other ways to look for these particles, and one of them is in underground laboratory experiments. So this is a completely different concept. Here you're taking advantage of the fact that you do have WIMPs in the galaxy. They're the dominant component of the galaxy if they are the dark matter. And if you have the right detector, then when you have this nucleus sitting here and the WIMP comes along and scatters off of the detector, it heats up the nucleus just a tiny amount. And people are trying to look for that because a weak interaction means a very small amount of energy deposited and a very small count rate, less than 1 count per kilogram of detector per day. So this is actually one of the ways, how I got into dark matter. I was at a winter school in Jerusalem, and this guy told me about some work that he'd been doing on looking for neutrinos, which are also weakly interacting particles. And next thing you know, I was a postdoc at Harvard, and that's me and David Spergel, and that's Andre. Oh, Andre, he's something else. He's Polish, but he speaks English, French, German, all at the same time. So he's gotten better, but he's pretty hard. He's a character. So we actually wrote some of the very first papers on these ideas of WIMPs. I did the calculations for how the WIMPs, I did the Feynman diagrams, the WIMPs scattering off of different types of particles in the different nuclei, and David did how WIMPs behave in the galaxy. And we also, so the calculations we did, we convinced people to start building experiments, and they're really hard experiments. So they have to be underground. This, for example, is the Gran Sasso Tunnel is outside of Rome underneath the Apennine Mountains. And so you have to be a mile underground to get away from competing signals from cosmic rays. So after we did our calculations, then people started building detectors, and it is a worldwide effort, even at the South Pole. So there's all kinds of experiments, and it's frustrating because most of them don't see anything, with one exception, DAMA, and I'm going to tell you about that. So in our original papers, we noticed something, which is that as the Earth moves around the sun, you're going to get a difference in the count rate, an annual modulation in the count rate. So you should get a peak count in June and a minimum in December, and so on and so forth. And this is what this DAMA experiment in that Gran Sasso Tunnel, this is what they see. So they've got 13 years of data, and I'm sorry, it's no longer a 9 sigma result, it's a 12 sigma result. So they're definitely seeing some annual modulation, but the question is what is causing it? And it is not the temperature in Rome. So it's really a weird situation because they won't release their data. So it's very hard. They give you, they process it themselves. So they won't let anybody look at the actual data. And that's really engenders suspicion. And the other thing that's weird is other experiments don't see anything. So I would like to show this slide. These are the group leaders of various experiments. Rita Bernabe, she's the principal investigator for this DAMA experiment that sees the modulation. Juan Collier, a different experiment, Cogent, and Eleanor Prele Xenon, which has the tightest bounds on these particles. And Juan, as he said to me, I'm a Spaniard caught between 2 Italian women. We have quite some characters in this business. So the weird thing is that I'm not going to take a lot of time to explain this picture. This is for different mass particles and different interaction strengths. To explain this DAMA annual modulation, you should be in these green regions, but according to the Eleanor Prele Xenon experiment, you should be below the green line, so it doesn't match up. But in order to put everything on the same picture, that's really difficult because DAMA is made of sodium iodide crystals and xenon is made of xenon liquid. So unless you know exactly what the interaction is, you can't plot things on the same picture. So this picture has some massive assumptions put into it. Oh, well, and then we go to meetings and have fun discussing these results. This is the UCLA dark matter meeting. That's the best one. And Rick Gateskill, the Lux experiment, also made a xenon. Yes, these are, oh dear, post-COVID will never do this again. Anyway, so to test DAMA, other groups are now building experiments using the same material as DAMA. And in particular, the cosine 100 experiment is working. So we'll know in 3 to 5 years other experiments as well. So this DAMA, this tantalizing hint of the signal from DAMA is we're going to find out what is going on with that. Yeah, that would be great if it were real, and we'll see. But in the meantime, I wanted to mention some other ideas we had for the next generation of dark matter experiments, and this one is just too much fun to pass up and not tell you about. So here you have a thin layer of gold, yes, with DNA strands hanging down. And what happens here is that the WIMP comes along, knocks the gold nucleus into the hanging strands of DNA, and it breaks the DNA. So these guys fall down. And thanks to the amazing progress in biology, we can actually figure out where these breaks happened, because you can sequence these things. You can make multiple copies. You can sequence them. You can identify them. So you can figure out what track this gold took. Let me make sure that you don't get the idea that the DNA is being broken by the WIMP. It's not. It's being broken by the gold. So, and by making a track, you can figure out what direction the WIMP came from. Now that's a big deal. That'll certainly help to make sure you know what's going on. Then you can identify, is it really a WIMP or not? Because we know in the galaxy how many we expect from which direction. So that will be really great if we ever get that going. You know, I'm not going to go on forever. There's other ways to look for WIMPs, which they annihilate, and the annihilation signals, when they annihilate among themselves, you end up with gamma rays. And there's an experiment that sees the Fermi satellite sees extra high energy photons coming from the center of the galaxy. Right in there is a little spherical region that could be from dark matter annihilation, but we don't know. So there's that unexplained excess there. So we have this excess near the galactic center, possibly from dark matter annihilation. We have this DAMA annual modulation, and then we have theorists trying to explain all the existing positive and negative results in terms of a particular WIMP interpretation. So we'll see what happens. And in the future, what we have to have is compatible signals in a variety of different experiments. And so that's what I'm hoping will come. But I have to tell you about my latest baby, which is dark stars. Namely, dark matter annihilation can power the first stars as well. It's another way to look for WIMPs. It's also a new kind of star. So I have to tell you about it. Well, yeah, there was a movie about the dark stars that predated our dark stars, but such is life. We didn't know. And so this is work that I did with Doug Spoliar and Paolo Gondolo initially. And the basic idea is that the very first stars to form in the history of the universe, which is when the universe was about 200 million years old, those could have had a really brand new kind of power source, not fusion. You would not have any fusion yet. Instead, you would have the power from dark matter annihilation. Now, these stars, I have to make sure to point out, they're made entirely of hydrogen and helium, so they're normal matter, but the power comes from the dark matter. And these things would start out about the mass of the sun, but then they could grow to be very large, even up to 10 million times as massive as the sun. And these supermassive ones would be really bright, up to 10 billion times as bright as the sun. And the next generation space telescope, the James Webb Space Telescope, might be able to find the biggest and brightest ones if we're lucky. So I'm really hoping that we're making predictions for what they should look like in the telescope, which is now supposed to launch, I guess, in 2023, keeps getting postponed. We'll see what happens. And the other thing that's cool about this idea is that once the dark matter runs out, then the dark stars, they start collapsing and getting hot enough for fusion, but in the long run would collapse to black holes. And that might explain the origin of supermassive black holes, which is a big puzzle in astronomy. So I talked about different ways of looking for WIMP dark matter with direct detection, indirect detection, collider searchers, or looking for dark stars. And I don't, unfortunately, have time to say much about dark energy, but the difference is that matter, it clumps together. It feels gravity in the normal way. The thing that we call dark energy, and there's probably no relation between dark energy and dark matter other than the fact that they're both dark. There might be, but there may or may not be. But dark energy is something that causes the universe expansion to accelerate. So it has a kind of anti-gravity behavior, repulsive behavior. So it's not any kind, it's not ordinary matter, it's not any type of matter at all. It's something completely new and completely not understood. So and so what is observed is that things are accelerating. Well, what's actually observed is that supernovae are dimmer than they should be, but the consequence is that things are accelerating apart from one another. And I only have time to end with a joke. So this is the World Science Festival in June 2011. This is me, Eleanor. These are three of us talking about dark matter on the stage, and these over here, these three talking about dark energy. There's Michael Turner, who will be speaking to you in a few weeks, and Salt Perlmutter, who discovered the supernovae being fainter, and this is Brian Greene, who's one of the best science writers out there. Glennis Farrar over here has written about the bullet cluster. Elena Aprile, the PI of the xenon experiment. But anyhow, so there's only one, we don't understand the theory of dark energy. We don't understand the nature of it observationally. We're going to learn some more in the future. The only thing we know is what I used to make a pretty good joke, if you ask me. Dark matter is attractive while dark energy is repulsive. So, so I will end with that. And here's my, this is my, I guess I was going to go back to my cosmic cocktail recipe, but I don't know if I'm going to find it again or not. So I wanted to end with that if I could find it again.
Well, that's great. Thank you, Katie.
Thank you.
That was outstanding.
Oh, I went past it. Okay, so there's my recipe. That's supposed to be 3 ounces of dark matter and 2 ounces of dark energy. It should really be only 2.5 ounces of dark matter.
It sounds so filling. It just
Ah,
Well, 3 ounces is
All
a
the
stronger
way.
brew.
right. Will it fit in this? That's great. You know, I saw that there was
Sure.
there's some questions.
What do you mean? You've got it in there.
Yeah, I do. Yeah, it's chock full. Vitamins too.
It's chock full.
Alex, you want to take some of these questions?
Yeah, so we got one from a YouTube viewer. If a dark matter cloud passed in front of a star, would the star be dimmed?
Well, the dark matter cloud. So
Be a really big cloud.
yeah, I don't know. I mean, you know, so dark, I guess our galaxy is a dark matter cloud, right? So it depends on how dense this thing is. Because in our galaxy, we do see stars nevertheless, because it's not dense enough to prevent the starlight. But if you made a really dense object made out of dark matter, yes, then the star behind it would then, like this, machos are massive compact halo objects, for example. If that's dark matter, then you would have the light behind that would be bent as it comes to you in the same way. So you'd have that lensing going on. So the dark matter doesn't give off light itself, but it does lens the light behind it. If, I'm not going to call it a cloud, if it's a condensed object made of dark matter, then it would lens the light behind it.
Okay.
Well, I know that we definitely want to hear more about the Queen of Sweden story. I mean, I want to hear more. I'm certainly interested to hear that.
Well, if I have the series of pictures to go along with it, it's really funny. But so I was invited. There's the Crawford. Okay, so let me back up. Last year, Jim Peebles was one of the people who was awarded the Nobel Prize. But uh-oh, my internet connection's unstable. Can you still hear me? I hope. So
Mostly.
going back 10 years ago, the prize, or at the beginning, there were anything that was too astronomical was not given the Nobel Prize. So Edwin Hubble got a postage stamp. He never got the Nobel Prize because astronomy was not eligible for the physics prize, okay? So therefore, there's another Swedish industrialist Crawford, who decided to give a prize in some of the other fields, including one is in astronomy every 3 years. So it was Jim Peebles, Jim Gunn, and Martin Rees won the Crawford Prize, and there was a conference of 20 people that I got invited to. That's the first time well, maybe one of the first times I got to Stockholm. And at the dinner, I was sitting next to the granddaughter of the Crawford, the industrialist. And she afterwards introduced me to her brother. And so I was taking pictures. I got a nice picture of the king, but my attempt to take a picture of the queen, I got a potted plant. And then the brother wanted a picture of himself with Licia Verde, who is one of the other women who attended the conference, and I managed to chop their heads off, okay? So he couldn't believe these bad pictures I was taking. And so he said, you know, you want a picture of the queen, come with me. So he introduced me to the queen. And so we started chatting briefly, and then she starts asking me, you know, what could you please define space? And my heart was kind of pounding, define space. Oh my God. So I decided to define outer space in the sense of if you leave the Earth, you leave the solar system, you leave the galaxy, go to some average place in the universe. I guess that's outer space. That's 10 to the minus 29 gram per cubic centimeter. That's the average density out there. And she just looked at me quite puzzled, and she said, that's not what the mathematician said. And so I was like, oh God. Now what do I do? So the conversation got all of a sudden this very awkward silence. And then I completely panicked. I said, the first thing popping into my head, I said, are you best friends with the Queen of Norway? Now you understand, it's her job to smile. Any queens are supposed to smile all the time. All of a sudden she went, ugh. I'm like, oh my God. And I kind of ran away. I got some pictures with her, okay? And then I kind of ran away. And I didn't know that was by complete coincidence the day of the 100th anniversary of the secession of Norway from Sweden. And I am not joking. I put and they
Wow.
lost the oil, right? So
That's hilarious.
So, oh God, I put my foot in it.
You discovered dark topics.
Yeah. Oh.
Alex, anything else?
Oh, I later got to take Stephen Hawking to meet the king. That was also an adventure.
How was Hawking to talk with when he was, not prepared to have something to answer you back with?
He had a team of nurses who knew him very well, and they would basically answer for him. So I mean, it took him a very long time, like 10 minutes, to make a sentence, which he sometimes did, if he wanted to. And but if, as you know, when he gave lectures, he would prepare in advance. And so we had a Hawking radiation conference I was director of Nordita in Stockholm, and one of the things we did was have a Hawking radiation conference, and he came along with 12 other luminaries, and he there's a new theory that he was promoting, and so he gave a talk about that there. And in answering questions it takes a very long time, but I mean, people want to hear it, what he has to say, So, but, yeah. And one of the administrative help at Nordita, they hit it off. And she took him she was one of the people who took him to the airport, and she gave him, they have these chocolate Nobel Prizes, so she gave him one and hung it around his neck. And he actually apparently really enjoyed it.
He's one of those guys that every time he come into a room, did people just like spontaneously clap? I mean, always. I mean, that would be the kind of thing with him, right?
Everybody got very excited. Yeah.
Alex?
Here's a question. Do we think dark matter is relatively smoothly distributed, or is it clumpy like regular matter?
Well, that's, you figures you would ask the thing I decided to skip. So initially smoothly distributed. But then there was an early period of accelerated expansion called inflation, So although it was basically uniformly distributed, there were some pockets that had a little bit extra matter compared to the neighboring pockets. And that's what this picture, the blue stuff in this picture is the dark matter. And so it's slightly clumpy, right? And then those regions that have a little extra stuff in them have more gravitational pull on the neighbors. And so they start, that's how the clumping starts. So it started out almost uniform, slight clumpiness. And as time goes on, let's watch these blue dots clump together. And this is what our universe, this is obviously from a simulation, a computer simulation. And the blue dots that you see here, you have sort of the stringy structures. And at the intersections of these strings, that's where the galaxies are. So this is supposed to be our universe today, and it pretty much matches what it looks like. So the dark matter clumped more and more as time went on, and then you ended up with galaxies and clusters of galaxies and super clusters and these filaments as well.
What is the Hawaiian name for that too? There's, I forget what it is, but it's the all-encompassing kind of view that you're showing here.
That I don't know.
Yeah, it's maybe Cal, do you know that one? Is that? I think he's muted there. No, I thought I should have said it
Are
before.
you talking about Laniakea?
Laniakea, that's it. Thank you.
What I don't know about this. Tell me about this.
Cal, can you explain it? But I mean,
Well,
that is, we're
I think
looking
you
at
can
it.
explain it better than I can. I've seen the name in print.
Oh, then yeah, I'm off on a tangent here. But this I understand is Laniakea is the largest structure in the universe, and that's what you are showing right now is the largest structure in the universe. So yeah, I wish I had some more background on that. I was hoping that you would know about it so I could hear more, but no, that's okay. But yeah, at least Cal knew what it was called and I didn't. Thank you, Cal.
Any other questions there, Alex?
There's a couple. Do we think that dark matter or dark energy transform into each other or into regular matter, like matter and energy do?
Yeah, that's the thing that is confusing about the names dark matter and dark energy. They're not related in the way regular matter and regular energy are, so that we don't think they transform into each other. So the dark out front means that they don't shine. That's what they share. Now, there are theories that people have proposed where they could actually be related to each other. There's some kind of, in addition to the four forces that we know about, there could be a fifth force. And so they could be related in some way. And some people have written down theories where they try to make that happen. So it's possible, but I would bet against it. But nobody knows. Dark energy is such a mystery. So the most popular explanation for dark energy is the cosmological constant. I mentioned that Einstein wanted a static universe, and the way he did it was to put in a cosmological constant. And he balanced that off against the matter and energy. But if you have a cosmological constant that's bigger than anything else in the equations, it drives an accelerated expansion. So ironically, although he later called the cosmological constant his biggest blunder, it is back to haunt us. It's really funny. And if it's true, then you have this constant sitting in Einstein's equations. And you can think of it as a vacuum energy, and vacuum energies are real. With for example, when you have two parallel conducting plates, with the vacuum in between them causes them to be attracted together a tiny amount, so that the vacuum consists of is particles and antiparticles popping in and out of existence. And this is a real phenomenon that has been tested experimentally. But so if you have exactly the right amount of it, that would explain the dark energy. But it is constant. Whereas, so we don't know. That's one thing we can test. Is the dark, does it change with time as we look into the past history of the universe? And that's one of the things first now, the Roman telescope that they're going to go after determine is their time dependent to the dark energy. also oh, my internet is unstable.
Yeah, I can hear the,
Daisy experiment. There's a bunch of different. Can you
it
hear me
sounds like you
still?
fell into a time warp there, the black hole of crazy vortexing and something happened. It's that Michigan internet. Oh, I think are you still
Okay,
with us?
well, the Roman telescope and the Roman telescope, other telescope, and try to express dark energy with time by looking back in the universe. It's change with time. It's not a cosmos.
Yeah, maybe we should end it there.
Yeah, I think all of your neighbors are streaming. So and
Right.
it's 9:30 now. So I think it's best if we end on a high note.
Yeah, I'm sorry. That's yeah, she dropped out completely there. So yeah, I guess that's pretty much that's a wrap
That's a
then.
forced wrap.
I'm glad but honestly, that was a great talk. I mean, that was really, there she's back again. But that was really, really interesting, I thought. And I'm glad we could get her.
It's always interesting when they talk about weird stuff we don't understand. By definition, that's interesting.
Right. Yeah, I don't know if she's coming back in. Oh, here. There you are. Hi.
Well, we're lucky on the timing. That's all I can say.
Yeah, I think so too.
Yeah.
Thank you so much, though. That was a great talk. It was fascinating. It was far more. You gave a lot more to it than I ever thought that the talk would be. So thank you for that. You're a fascinating speaker. And she's frozen in time. But it's a beautiful smile. Aw. Anyway, well, I'm glad it worked out this way. So let's stick a fork in this thing. And again, thank you, Katie. Thank you so much. Thanks for everybody that attended. And again, we've got a great one next month and every month. So thank you very much. And there it is.
All right.
Thank you.
Thank you.
See you next
See you all soon.
Thank you for